Hey math people, it's time for lesson 77. I'm going to start off a little bit differently here. In the email I pointed you to one of my other videos that I made for pre-calculus. That was law of sines and law of cosines. I just want to let you know that at about the 13-minute mark, just past that, there we go, that I have an explanation of the law of cosines you might want to check out. So it would just be like the last 5 minutes of that one, and you'll get a good review of what I'm going to go through on the board. I also linked to, in the email, a short proof of Heron's formula, but it's missing an awful lot of steps. So I just want to let you know that in the past, I've worked out the whole proof, and I have that right here in my greedy little hand. So it took me like 4 pages of some pretty tricky stuff, and I took some tricks from Euler, some of his stuff that he did in his work to eventually solve for the thing at the end. So I'm pretty proud of that. It was kind of fun. I sent it to Willem. He cleaned it up a little bit. And yeah, I hate it when they say 1, 2, skip a few, 99, 100, and approve. So we connected all the dots. It was pretty cool. Okay, law of sines, law of cosines. The law of cosines is a rule that you can use to solve the missing parts of triangles given these two particular conditions. Now, law of sines, we used the other stuff. We used, I forget, it's in the video. We used the other conditions. But this one's if we have side angle side, which would be, you got your triangle here, and you're given this side and the included angle. This is a really good one. Side angle side is useful for lots of things. So you got, in this case, we've got angle A in between side C and B, right? It can't have angle or side A because that's opposite of angle A. So you've got side angle side, we can use this law. Also, if you know all 3 sides, and usually we think, oh, 3 sides, huh? Well, we can just use Pythagoras for that. And we're like, no, actually we can't. Only in very specific cases can we use the Pythagorean theorem. Down here are the formulas that get used depending on if you have angle A, B, or C. You'll use one of these. But I want you to look at this last one here. And you can see the whole thing is the law of cosines. And the front part of it, though, is the Pythagorean theorem. You've got this extra bit here that's kind of a bit of a corrective, depending on if you get an angle bigger than 90 or an angle less than 90. But if we put in 90 degrees in here for cosine angle, the cosine at 90 degrees is 0. So this whole minus 2ab cosine c stuff disappears when you have a 90-degree angle. So the proof will say this just really in passing, but the Pythagorean theorem was when you got what's called a degenerative case of the law of cosines. That means it's when stuff, part of it breaks down and becomes 0. That's all that you're left with. It's kind of a special case of the whole thing. Now, I'm just giving this to you for this particular setup. If I was drawing this picture, I would be solving for A. That's my unknown. I don't know A, and I don't know angle B, and I don't know angle C. So I would use this. A squared is B squared and C squared. B and C would be given sides of the triangle, minus 2 times B times C, times the cosine of angle A, which is also given. Or, I guess if you wanted to solve directly for A, you could take the square root of both sides. Slop all of that information into a formula, and out would come your answer. Same thing with these other ones. These are just if we're trying to solve, if maybe the letters have been rearranged, so we have maybe angle A and angle C and angle B. You just look at the given information, and you don't have to use A, B, and C. You can use whatever letters are given, as long as you have 2 sides and the included angle. Okay, that's super important that that A there is the included angle. It's the angle between the two other sides bits of information that you're given. So you should probably pause and write these down. We got a couple of fun things there. We changed this so we can solve for A, and we showed that the law of cosines is a degenerative case of it. When cosine is the angle is 90, then this part disappears and we're left with Pythagorean theorem. I'm going to clear it off because I know these. I know these things. Side, side, side is a really cool condition. Okay, side, side, side is a cool condition. It's a little clunky on the math here, but I'll just do it once, and then you make sure that you write down what I've got. Well, Heron's theorem gets to that. Anyway, I'm going to take this version of the law of cosines, and I'm going to solve it for the angle. If I'm given all the sides, I don't have any of the angles. And I need to start somewhere. I need to solve for three angles. All right, I got some missing information there. If I know all three sides, then the things that I have to search for would be the answers to those. So I have this formula where I've been given the three sides, and I need to solve for an angle. So I'm just going to start moving things to the other side and solve for this bit right here. That means I'm going to subtract b squared. I'm going to subtract c squared from both sides to get me a squared minus b squared minus c squared. That leaves me with negative 2bc cosine of angle A. And now I'm going to divide both sides by negative 2bc. Just using algebra, right? Once I do that, then I'm left with the cosine of A. But my goal is not to get the cosine of A, my goal was to get A. And so we're going to do the inverse operation. We're going to take the inverse cosine of both sides. The inverse cosine of cosine is just that angle. So here we go. Here's one of the ways we could write the rule for getting to that first angle available to us, angle A, if we are given all three sides. Now, another way to write this would be like this. I don't usually like to write the negatives in the bottom, so what we're going to do is we're going to switch the signs. Okay, we're going to switch the signs on it and then rearrange the parts. So if I kind of move that negative, pull it out, and then run it through the top, this is what I'll get. Negative a squared plus b squared plus c squared, or maybe better, b squared minus plus c squared minus a squared. And you would see this kind of setup that pops up often in the proof for Heron's formula, which is derived from the law of cosines, at least the formula for the area of a triangle given three sides. So you should write these down. That this is what you need to do if you have the side, side, side condition and you want to start solving for angles. The other three that we did previously were if you have side angles side and you're looking for the third side. Okay? So with either version of this same rule, you're going after one additional piece of information given the other information that you have. And once you have used the law of cosines to get one of these things, really it's probably more convenient now to go and use the law of sines, where we compare sides with their angles to derive the other angle, and then you can use subtraction to find the third angle. There's some good examples of that in your book. There's also, if you watch that other video, I'll work a couple of problems through with you there. Okay, now we've also got the fact that the area of a triangle, the area of a triangle is where the thinking came in order to get this theorem. Let's see, this is side B, that's side C, that's side A. We know that the area of a triangle is 1/2 base times height. And that's really nice if we get a triangle like this, right? Because the base and the height are 2 of the sides, and we take half of that. We take half of that because if we just said base times height, we would have a parallelogram, and that'd be pretty easy. But we only have half of a parallelogram when we have a triangle. Now, I think you see in this triangle up here, the base is easy, it's B. But the height is not so easy because we don't have a right angle in there. So what we do is we drop a 90 down, and we're going to call this H. And then what we're going to do is we're going to take the information that we do actually know, and we're going to derive something that's equal to H. So I'm going to go from angle C, though I could go from angle A. It doesn't really matter. And I could say that C, well, I guess I need opposite over hypotenuse. So the sine of C equals H over A. And I could turn that around and say A times the sine of C equals H. So now I have something to replace H with, 1/2 B, and then I can put A sine C, opposite over hypotenuse. Okay, so I'll explore that a little more in that other video. I'll draw a better picture on my calculator. And then we go like this. There's some interesting substitution, and then we go dot, dot, dot. And again, you check on Heron's formula. But we get to this expression that also will give us the area of a triangle. And this is called Heron's formula. It takes, first of all, a special thing in geometry called the semi-perimeter. The semi-perimeter is taking half of the perimeter of a triangle. Okay, I've looked this up on Wolfram Math World, and they've got an explanation there of what that's used for. It's a way of kind of, I don't know, not averaging, but it takes half the perimeter, and that's useful in geometry. It takes this value and they call it S. Now, Heron's formula for the area of a triangle looks like this. Once you've figured out what S is, given you've got all 3 sides, A, B, and C, you're going to multiply the semi-perimeter by S minus A times S minus B times S minus C. You take the square root, and out comes the area. So this one's pretty clever because it'll work with any triangle. You don't just need a right triangle in there. It'll work with any triangle. So you don't need any angles whatsoever. You just need the sides. So you can take one of those superhero triangles, and you can throw it into here, and you can find the area. And you can see how the superhero triangles jive with this story right here. So the first thing you gotta do is you gotta solve for S. You're gonna take the average of, well, it's not really the average, it's the semi-perimeter of the 3 sides, and then you're going to take that number, you're going to plug it in with A, B, and C, and take the square root, and you get the area. Okay, that's pretty cool. And again, I got some examples for you in the other video, but we could do it with a 3, 4, 5 triangle pretty easily. It's just math, right? It's just math. You're given a formula then for solving any triangle. Now, I guess maybe I'll do one from the book. Maybe I should do 2, one from each condition. So hang on to those formulas, and we'll do a couple of examples. Okay, I got a couple of examples for each condition. Well, one example for each condition. Also want to mention that there's going to be something in vector land called dot products that uses a form of or equivalence to the law of cosines. When I saw that doing vectors in physics and saw that basically this was the same thing, I was like, you got to be kidding me. Vectors, like, let's add these two vectors together, or multiply these two vectors. You know, like vector 1 and vector 2 with an angle between them, or two forces pulling on something. And then I was astonished to know I could use the law of cosines, or a version of it. I thought that was pretty cool. Lots of applications. I was astounded by how many connections there were from different things that I was trying to do. Okay, so this is the first one here, and we look at it and we got the condition where we know this side, we know the angle, and we know this other side. That is, we know side A, we know what side B is, and we have angle C. Side angle side condition. So if we want to solve for C, that's what the formula gives us right away. I'm going to use the square root version of that formula. We go a squared and b squared minus 2 times a times b times the cosine of the angle C, and that would be cosine of 27 degrees. And from there, we can just go right away to plugging this stuff into the calculator. Square root of 20 squared plus 13 squared minus 2 times 20 times 13 times the cosine of 27. Now I need to double check and make sure that I'm in the right mode. I'm in degree mode, so I'm good. And I hit enter, and it tells me that it's about 10.28. And the picture looks like that jives pretty well. So there we go, I got a third side. Good for me. Now that I've got that, I can go and look at what I actually do have, and I can either go after angle A or angle B. I'm going to go after, I don't know, I'm going to go after A. Okay, so now I'm going to use the law of sines. That is, sine A is to side A 20 as the sine of C, 27 degrees, is to side C, which we said is about 10.28. So again, I only have one unknown now at this point because I selected the information that I had. I got to solve for A, so I'm going to multiply both sides by 20. And then I got to take the inverse sine of both sides. So I've got inverse sine, which my calculator is happy to do, of the fraction 20 times the sine of 27 over 10.28, close the parentheses, and that tells me that A is about 62.04 degrees. Okay, that's great. 62.04 degrees. Well, it doesn't look like it, does it? And here's where one of our problems is that it's not actually 64, it's the other buddy of it that's 180 degrees minus 62.04. So maybe I should have tried to solve for B, but I can just go 180 minus that answer, and I get that the actual answer here is 100, it's about 118 degrees. It's pretty close. Now I've got two angles, I can figure out the third. I'm going to quickly double check that. I'm going to go back here and I'm going to use the information. I'm going to go after it the other way. I'm going to go after angle B here. That is, given that I've got the sine of 27 matches up with side C, about 10.28, then I can go after the sine of angle B, and because I know that side B is 13. And now I'm going to solve for B by multiplying both sides by 13 and then taking the inverse sine of both sides. Now this one will only give me one answer, and it'll give me this small one, which I would be looking for. So inverse sine of 13 times the sine of 27 over 10.28 in parentheses tells me that that angle is about 35. And let's see if that jives with what we've got here already. 27, 118, and 35 shall all add up to 180, and they do. Okay, so I solved for the missing side, and then I used the other law, the law of sines, to find the missing angles. If I find one angle, I found all three angles because I had two angles, and two angles means angle, angle, angle. They may only ask you for one of those things, but I just want to show you can find out all the things using the law of cosines first, and then using that information to match up sides and angles to use the law of sines. The second one is the other condition, side, side, side condition. So we're going to go and use that alternate version, and where we're going to find angle A, and I'm going to use the second one where we have the inverse cosine of b squared plus c squared minus a squared over 2bc. Okay, so we'll go after angle A first. We don't know any of the angles. We go after any of them that we wanted to. I can go after angle A first. Inverse cosine of, this is B, and then this is C, and that's A. So we're going after 30 squared plus 18 squared minus 14 squared over 2 times 30 times 18. Just use the information given and take the inverse cosine of 30 squared and 18 squared minus 14 squared over 2 times, does that bother any of you? 2 times 30 times 18 and parentheses equals about 17.85 degrees. We could either use another version of this to solve for the other angles, or at this point use the law of sines. I would use the law of sines and to go after angle C. Yeah, because now I've got, I got a side angle side condition here, but nevertheless, I'm going to go after angle C. So the sine of C is to 18 as the sine of 17.85 degrees is to 14. Okay, I'm using my little analogies here, and then all I have to do is times both sides by 18, and then take the inverse sine of both sides, so that C equals the inverse sine of 18 times the sine of 17.85 over 14, and my calculator will be happy to do the math there. 18 times the sine of 17.85 over 14 in parentheses equals about 23.21 degrees. And once I have that one and that one, I can do a little bit of subtraction, and I can find out that third one without getting too complicated. So there you go. Given the three sides, I can find one of the other angles, and then I can use law of sines to figure out the second angle, and I can use subtraction to figure out the third. Last thing I would do with this is I could find out the area of this triangle right here by using Heron's formula. So first I got to figure out what's 1/2 of this, what's the semi-perimeter, 18 and 14 and 30, to get this S value. So that's 30, 40, 50, 62. Half of 62 is 31. S is 31. And now I'm going to throw that into the formula. Area of the triangle equals 31 times 31 minus 30, 31 minus 18, and 31 minus 14. Doesn't matter which order I go in order to find the area there. So big square root 31 times, looks like 1 times, what's 31 minus 18? That's 13. And 31 minus 14 is 17. And I get an area of approximately 82.77 square units. I kind of like that. Makes you feel pretty powerful that you just give me the sides, I'll give you the angle, or I'll give you the area. So Heron's formula is pretty powerful, and it's pretty ingenious proof. Trust me on that one. Okay, that's it for today. Shows you how to do both those kinds in both conditions. Make sure you use those formulas that I gave you. Refer to those often. I'm just trying to see if they're on anything else here. No, they're probably on a geometry sheet somewhere, but I don't have one of those right now. Okay, hopefully that's enough for you to get working on your stuff. We'll do math chat if you need some help on the details.